Greetings, everyone. Welcome to the next edition of the Montreal Machine Learning Optimization Public Seminar. Today we're delighted to have Aaron Defazio, who is a research scientist at Facebook AI Research in New York, and he's going to be telling us about adventures in optimization for large-scale deep learning. And without further ado, Aaron, please take it away.
Awesome. Thanks, Mike. So yeah, I'm going to be kind of talking about a little bit of a grab bag of topics kind of related to my journey of trying to understand various aspects of how we do deep learning training in practice. So this is kind of not the toy problems people look at in optimization papers, but we're talking about like large scale, starting at 8 GPUs and upwards, the kind of training people are actually doing in practice and the techniques that they use. And one of my kind of research agendas has been, understanding and attempting to kind of improve on the techniques people are using there, bringing things on kind of a little bit more of a theoretical foundation. So the kind of topics I'll be looking at, number one. So I'm gonna start with momentum, and because this is kind of key. It's used everywhere. All the techniques we have use it, and the theory behind it is very unsatisfactory in some ways. So I'm going to kind of talk about how, with some collaborators, we've been trying to understand momentum and how some of the assumptions people make, like the idea that you can just take ideas from the convex case and bring them to the non-convex case. It often works, but momentum, I think, is one of the situations where it really acts fundamentally different. And a lot of the assumptions and analogies people draw from momentum that apply in the convex case just don't make sense in the non-convex case. We've got to use different tools for understanding what's going on there. I'm also going to talk about a adaptive method that I worked on, where I was taking some insights from practical use of adaptive methods, as well as this momentum work that I talked about, to try and essentially modernize AdaGrad. And we had some success there. We're calling the method MadGrad. So I'll kind of describe that in a fair bit of detail, because there's a lot of interesting ideas there. If you're a practitioner, you might be interested in using that algorithm, but you may also just be interested in how you can go from AdaGrad, which is a very sound method, especially in the convex case, and kind of modify it without losing the soundness, at least in the convex case, but bring it up to matching or exceeding performance of methods like Adam in the deep learning setting. And I'm going to rant a little bit about how we're doing all our experiments wrong in optimization papers for deep learning, and how we're probably going to continue doing them wrong. And I'm then finally going to talk about a way of kind of preconditioning neural networks by adding constants to them at kind of design time. It's kind of like an ambitious idea, which doesn't actually work very well with the networks that we have, because they're kind of almost too easy to optimize at the moment. But I'll talk a bit more about that later. So let's start with momentum. The first thing I kind of want to get off my back is this analogy. We keep teaching our students about momentum by drawing these metal balls rolling down imaginary hills, landing in valleys. And I want to kind of argue that this is just completely the wrong way of thinking about momentum. And these physics analogies can be interesting, but it kind of breaks down when you try and go into the details. And when you try and analyze these methods, the analogy doesn't carry through to the analysis. But firstly, let's just think about what momentum is. So one of the ways of understanding a method is by rephrasing it. Often, especially with simple optimization methods, there's multiple ways of writing them down in equational form that are equivalent, and these different ways give you a different idea of what's going on. So the momentum analogy, the physics analogy of a ball with momentum rolling down a hill, applies to one of these equational forms for momentum, but doesn't really apply to the other forms. So I'm going to argue that the forms that we typically use are maybe not the correct form for analysis, and see where we kind of go from there. So these are kind of the three common forms of momentum. You see these in a lot of papers. Sometimes they go by different names. So the heavy ball form at the bottom is sometimes kind of the standard form. Other times it's kind of the momentum form at the top. So I'm assuming some kind of familiarity with optimization theory. I'm not going to be presenting any proofs in this talk. I'm just going to be kind of presenting some algorithms and one or two theorems. But you need to know the kind of basic notation. So here I'm working in stochastic setting. So I have the nabla f as the gradient of f, and I'm passing as an argument xi just being the random sample that you're sampling. So this k would typically be a gradient or mini batch sampled at the kth step of the optimization method. So just think of that whole nabla f term as just being the stochastic gradient at the step. So this first form is what's implemented in most of the optimization frameworks we use. Sometimes there's the option to add dampening. This it doesn't actually change what the method does, but it changes the parameterization. So if you're going from one form to the other, momentum versus the damped form, you need to be careful with how you set your parameters. Like for instance, we would typically use learning rate like 0.1 for training a lot of computer vision problems with momentum. That's if using 0.9 momentum. And if you go to the damped form, you're going to have to change that learning rate to 1 instead. So all of these forms require different parameterizations. And this is true of the heavy ball form at the bottom as well. But the form I want to kind of focus on, which is lesser known, is called the stochastic primal averaging form. And this initially arose in some papers that didn't recognize initially the link between this and momentum. So let me go through this carefully. On the previous slide, we showed a method where we average the gradients over time using either an exponential moving average or a decaying moving average. So here we do a moving average of the iterates, that is the x points, which I'll call the iterates for the purpose of this talk. The Z sequence you see looks a lot like a regular SGD update with no momentum, except this gradient is evaluated at the X sequence. And that X sequence is a simple exponential moving average. Let me go back to the previous slide and just kind of show the relation here. If you look at the damped form in the middle, by exponential moving average, I just mean one of these updates where you multiply the previous value by a factor that's less than 1. In this case, you can think of it as being about 0.9, something like that. That'll be beta in the middle equation. And then you add on a new term, which is multiplied by 1 minus beta. So the kind of magnitude of this term shouldn't grow over time. It really depends on the scale of the gradients. This is why you add new values in with damping. And this is a classical exponential moving average formula. So the SBA form uses a moving average of the iterates instead. So this was also analyzed in non-smooth case in the paper that I mentioned there at the bottom by Tao. And it sometimes crops up in various places in various forms, but the link with momentum is not well known as far as I'm aware. And I've been kind of exploring this with some of my collaborators recently to kind of get to the bottom of this. Now, when you look at this form, it does seem a little odd because there's not an obvious physics analogy for averaging position. So this is why kind of the physics analogy starts to break down here. But what you do find is this X sequence. When you try and analyze these momentum methods, this X sequence seems to be the more useful quantity that appears in the proofs. Now, I'm a big believer that if quantities appear in the proof, that maybe we should be including the method as well. And in fact, some of the earlier methods that analyze momentum methods effectively transform the Z variables into something like X, just for the purpose of proof, without using the method. So let me talk a bit about the mapping here. So this is a whole bunch of equations, but essentially, when I say these forms are equivalent, I mean that you can, for any set of hyperparameters, map exactly between them with these simple formulas and back. And this will give you exactly the same X sequence and Z sequence. And these formulas are pretty short and simple. And if you're using fixed hyperparameters, like your etters and your betas don't vary over time, then these formulas simplify even more. And particularly if you look at that bottom formula for beta, if you think of eta as not changing over time, beta is just 1 minus C. So you can think of C here as being 1 minus the momentum amount. So if we were trying to use, as we often do in deep learning, momentum 0.9, our C would be 0.1. So why do I think this is kind of the right approach to take? Well, as I said, it comes up a lot when you try and look into these methods. But there's other reasons. So let's talk about variance. Often the most useful form of an optimization method in terms of the equational form is the version that is most easily adapted to new settings. So here you can look at the setting of just adding a projection operator to a momentum method. Now, if you try and add a projection operator to the other forms of momentum that I showed, you run into all sorts of difficulties in analyzing them. Where when you add it in this form, everything just follows through exactly. You get the same convergence rates just as you would expect from adding a projection to SGD. So there's really no difficulty here for kind of adding extra complications on top of the method. And you can kind of do analysis here. You get virtually identical rates as what you get with SGD. So no need to kind of go into the details here. Here's some just formulas that I established in the papers with collaborators at the bottom, working with Robert Gower and Othmane. And basically, these rates are comparable to similar rates established for SGD. So the first equation, in the convex but non-strongly convex case, you essentially get 1 over square root k type convergence with constants that are very close to the regular SGD case. The strongly convex case, that's also what comes out. What's the next slide? What I want to point out here is that this method is effectively iterate averaging applied within the method. So typically when we analyze stochastic gradient methods, we analyze an average of the iterates for the final convergence rate. Not always, but typically. And often we do that with some sort of exponential average or weighted average. Now in this form, where essentially we have an exponential average or weighted average directly within the method. And what you find when you try and analyze this method is you get very similar rates for this inline average as you would get for this offline average that you would typically find. And in fact, the weighting sequence you should use, the CK sequence here, corresponds to essentially the same weighting sequence that you would use in this offline average. So this theorem 3 here, we use this CK sequence of 4 over k plus 4. This gives you a front-weighted average, which is very similar to the front-weighted average people use for SGD to get that kind of very tight constant. So another reason to kind of consider this method is it's actually kind of very similar to a form of accelerated gradient descent that people often analyze. So there are a lot of ways of writing down Nesterov's accelerated gradient method. In fact, I think in one of my papers I have a table of 7 different ways of writing the method that are equivalent, and I missed one, so there's at least 8 that I know of now. But this is kind of the form that I think is the easiest to analyze of the accelerated gradient method at the top here. And you can see it's actually very similar to the SPA form, except it has an additional interpolation. Now, there's a lot of symbols here, but when you look at this first row, it's not an exponential moving average. The bottom equation, the update for x, is an exponential moving average. So the y update here is an interpolation because you're not looking at including y from the previous step when you write it this way. So it slightly shrinks the value back towards a past value. So yeah, another reason why it's useful, extensions. But it also arises in lots of other places. So I think probably some people on this call here have looked at this conditional gradient method. This has been kind of like popular in the optimization community because there's some very nice theoretical properties. But if you see, this exponential moving average within the conditional gradient method, often those moving average sequences you use are very similar to what you would use for the momentum method. So I'm going to make the claim that all the analyses for the conditional gradient method actually already include momentum. So you've been using momentum all along. Maybe that's disappointing if you've been trying to add additional momentum to the method. But I think it's kind of satisfying. So in my mind, this kind of moving average or the iterate sequence is momentum. And anyway, it kind of appears in optimization. We should consider it as a an extension of momentum. And if we look at it through that lens, analysis becomes easier, and we can link it to other methods more easily. So if this SPA form, stochastic primal averaging form, has so many interesting results, can we kind of move on from these old forms? Well, it's not so simple. When you implement the method in this form, as I mentioned before, if you're using fixed hyperparameters, which is typically what we do in the analysis of these methods, there's really no difference between the various forms. The implementation of one form can just be mapped to the implementation in the other form, same iterate sequence, no difference. But in practice, at least for training deep learning models, and also often in other settings, we use non-fixed hyperparameter schemes. Typically, this would correspond to a decreasing learning rate sequence, is common. When you try and do this in this primal averaging form, interesting things happen. And I have a paper on this, which will not get accepted anywhere, probably, where I explore these results. So let me show you some plots, and this is very interesting and surprising to me. So what I did here on the left, I show SGD, and then I map the hyperparameters using that equation I showed you a few slides back that lets you map between the hyperparameters. I map it to the SPA form. Just looking at the left two plots. And what you can see is when you decrease that learning rate, the alpha in the momentum method, it does not behave in a reasonable way in the SPA form. In fact, what you see is the learning rate of SPA starts growing, and the momentum starts shrinking. So this is not intuitive, and this in fact will break the analysis, because when we analyze the SPA method, you can't analyze it with a linearly increasing learning rate, linearly increasing momentum rate. So if you believe in this this rationale that we've been doing momentum all along the wrong way, you should be just bang your head on the table right now, because have we been doing our learning rate decreases wrong for the last few decades? Because it certainly seems that way when you look at these equations. And in the right two plots, I kind of experiment with the obvious other thing. What happens when we decrease momentum? When you do that there, you also see this kind of linear change in the hyperparameters for SPA form. So this is worrying. It worried the hell out of me. So I want to show you a few other plots where I explore how you can change these values and what happens there. Was that a question? Popped up?
Yeah, I had a question.
Yeah.
I think I kind of missed the point of this slide, and it seems important. So what is the value we're plotting on the y-axis here?
Oh, yes. So it's the value of the hyperparameter that makes the two forms equivalent. So, if you look at that very left plot, that is a plot of my learning rate over time during training and my momentum parameter during training. So here I have a learning rate that starts at 1, and then I decrease it tenfold during training. And I keep my momentum at about 0.9. And when you do that, if you look at the second plot, you see when you do this equivalent mapping where you change the hyperparameters of SPA to exactly give the same iterate sequences, you find that the learning rate in the SPA form diverges linearly. And likewise, the momentum sequence starts to shrink linearly.
Does that mean that if I want to use the SPA form in order to get the exact same, I guess, sequence of steps as the SGD plus momentum form, these two lines in the second plot are the hyperparameters I need to use? Yes,
that's exactly what it means.
Okay.
Yeah, and that should be worrying you because it's a bizarre sequence. So on the next slide, I kind of do the opposite. So in the next slide, I set the SPA sequence hyperparameters and see what happens with SGD. So let's do that. These plots are of the same kind of form. So I've got a few different ones here. And the worrying thing is weird stuff happens most of the time. So let's start in the top corner. In this top corner, you can see if you look at the SPA plot that I decrease that learning rate. Learning rate by tenfold. What happens in regular momentum form? You get this huge spike in the momentum value, and that's bad because our momentum value should normally be between 0 and 1. So the fact that to get this equivalent, you've got to make it bigger than 1. It's a head scratcher. So don't like that. So then in the top right plot, what do we do here? We keep the learning rate the same, but remove the momentum. So CK is kind of like 1 minus momentum. So if we push it to 1, it's like getting rid of the momentum. This is a bit more reasonable. It's a bit more reasonable. So here the learning rate alpha k in the regular form jumps by 10-fold and the momentum disappears. So that's not too worrying. And this kind of suggests maybe we should be looking at when you write momentum normally in the form that I've got in that equation on the left side of the screen now. We could consider actually both increasing the learning rate and removing the momentum at the same time. Seems like kind of a reasonable thing to do. In the bottom left plot, we also change both at once. So if in the SPA form, what happens if we decrease the learning rate and remove the momentum? This also gives you a weird spike in the learning rate in regular form. So what happens if you want something reasonable to happen in both forms? Now, the problem with that top right plot where I just get rid of momentum is that's really not, it's not a usable thing because we can only reduce it to a certain amount, right? Once we got rid of all the momentum, we can't get rid of it further. So this gives you a learning rate scheme where you can't decrease the learning rate very much after a certain point. You would have to basically at the first time remove the momentum, and then second time you want to reduce the effective learning rate, you then actually reduce the learning rate. So it's a bit weird. A solution in between the two is this bottom right plot, where in SPA form, we gradually reduce learning rate, gradually remove momentum. And then if you look at the this SGD typical standard form, SGD plus M, then we get something where our learning rate effectively stays the same, but we gradually remove momentum. Now, I'm going to argue that this is actually what we should have been doing all along. Everybody has been doing everything wrong. This is how we should be doing our learning rate schedules. Now, the caveat there, the asterisk, is these aren't enormous differences, and they only appear at the boundary of when you change your learning rate. So it's very likely that if you change your SGD method to use this new scheme I'm suggesting here that makes a lot more sense theoretically, you'll see tiny difference. It only affects a few stops of the method. May not be any difference at all. But it has some benefits for theoretical analysis and some practical benefits. So I know this is kind of a lot of lines and equations here. So if there are any questions on this slide, please ask. I'll give people a chance here. So just to summarize, I'm kind of proposing here that the right thing to do, at least when you look at this analogy between the two forms, is decrease the learning rate and the momentum parameter when viewed by viewing with the SPA form. Viewed from the standard momentum form, we should be gradually reducing our momentum parameter instead of our learning rate. Up until the point where you have no momentum, and then you should go back to reducing your learning rate. No questions? I'll continue.
Actually, Aaron, I have a question.
Yes.
So I think all this is very interesting, and it's question our intuitions. Just the thing I'm missing is in the bottom right plot. Why do you argue that this is the most sound scheduling?
So I'm kind of arguing by plot here, not exactly rigorous, but I'm trying to say that this scheme makes sense when viewed from both viewpoints of the method. So both in the SPA form and the regular form. And not only that, but as I will show in a few slides, this is actually very sensible when you actually look at the analysis of the methods. In fact, this is the only correct thing to do when you actually look at the equations. So this is backed up rigorously by the Lyapunov analysis. But it's motivated by this simple fact that you want your method to do something reasonable in every formulation of the method.
I see. Thanks.
Yeah.
Can I ask a quick question, Aaron?
Yeah.
Okay. Yeah. So I know at the beginning of the talk you said, you kind of pointed out that maybe it's not the right thing to do, and it's maybe bad that people are taking kind of intuitions from the convex setting and the deterministic setting and just applying them in the non-convex setting. But I'm wondering, so here, and so I'm going to make this analogy, but even though you said we shouldn't, But I'm just wondering, because I think in the strongly, or the, sorry, not strongly convex, but in the convex setting, I think rather than decreasing the momentum, you want to increase it during training to get the acceleration guarantees. Why is, well, yeah, can you explain maybe some intuition about the differences of why you wouldn't want to do that maybe in the non-convex and stochastic setting?
Yeah, so in fact that you're talking about the situation exactly what I was referring to. So if you look at the, let's go back to the theory. So I gave you these formulas. These are for the convex case. And these absolutely suggest that you should be decreasing the momentum. So this CK sequence is like a 1 minus beta. So it's 1 minus momentum sequence. So in both of these formulations, we're using a CK that decreases over time, corresponding to a momentum value that would get closer and closer to 1. And this is because in the convex case, momentum is just averaging. Now, this goes against everything we tell the students. We say that momentum is acceleration. Now, I argue that momentum and acceleration are two different things, right? We know the regular momentum equations only give acceleration with very precise choice of hyperparameters in very precise settings, not in the general convex case. So here, when you're looking at stochastic convex problems, momentum is averaging. And what do we do when we analyze SGD? We look at an equal weighted average of the iterates over time. Give every iterate equal weighting. That is exactly equivalent to the weighting I use in this first theorem, CK 1 over K plus 1. That is, when you look at the expansion of what that actually does, it weighs every iterate you saw during optimization with equal weight in the final output point. But yes, this doesn't make sense in the non-convex case. And when you try and analyze these methods in the non-convex case, you want to do something vaguely close to what people do in practice. And in practice, people use the fixed momentums of values like 0.9 and 0.99. And this is not, I should say, they have a good reason to do this. Practitioners have tried every possible combination of how to do this, and this is what works. What I can tell you is when you look at the stochastic convex case, the weighting sequence in this theorem is actually more effective than fixed momentum that people use in the deep learning setting. So if you actually implement this and test on nice convex problems, you should be doing this kind of decreasing momentum.
Okay.
So yeah, so this is exactly where the divergence occurs. So you hit the nail on the head here. It's all to do with the way we use momentum. And this is backed up by the theory in these two different settings. You get very different theory. So you certainly can't carry across these momentum sequences to the non-convex case and still get reasonable results.
Quick follow-ups, if I may.
Yeah.
So
yeah.
It's about a detail I might have missed. Is the statement that these particular choices for eta and c in these theorems are optimal for a certain setting?
I don't know about optimal. You get rates as tight as the standard analysis of SGD. So I'm not sure about if they're actually optimal up to constants, but they're otherwise like big O optimal in the settings you're analyzing.
That you get on N, for example, is tight.
Yeah. Yes. For in these two cases, but these are I should say that it's within like the non-accelerated method class. These are both for non-smooth problems, so you're not looking at situations where you can get acceleration or anything like that.
Right.
Yeah. So I didn't want to go into the details too much here to keep this kind of more of a practitioner-friendly talk rather than a theoretician-friendly talk. But yeah, so here we're assuming we're not in the smooth setting; we're in the non-smooth setting. The functions are G Lipschitz, and yeah. So yeah, maybe I should have talked a little bit more about that. Thanks for that question. So let's look at let me dig into a little bit of the theory. And everything that blue box, you can just imagine it's a bunch of random symbols because it doesn't matter for the purpose of this talk. But essentially, you can do an analysis of the SPA method using Lyapunov tools. And these techniques are not too non-standard. If you look at SGD, this top formula here, this is the kind of one-step Lyapunov analysis you get when you do this sort of analysis for SGD. So you get a Lyapunov function lambda, and you get these extra terms, and you're bounding the gradient. Now, I don't want to go into kind of detail of this, but what I want to point out is how the momentum methods kind of differ when you do this kind of Lyapunov analysis. So what I want to point out is focus on the SGD equation. We're bounding squared gradient, and we're doing it with 2 extra terms on the right. So ignore the capital lambda terms, they're the Lyapunov function terms, but we have these 2 other terms. Half LG squared, this is effectively the noise. And RK is 0 when your hyperparameters don't change. So effectively, for the purpose of analysis, where we typically assume fixed parameters, you just ignore RK, it's equal to 0. So SGD basically has gradient squared term on the left and noise term on the right, that's half LG squared. So when we analyze this SPA form, we get something a little bit more interesting. Now, on the left side of the equation, instead of getting gradient at xk, we get an equal average between the gradient at xk and zk. So that suggests that when you're picking the final point that you should return from the method, rather than using one of the sequences or the other sequence, you could just sample 50-50 probability between returning the xk or the zk point. So they're each weighted by half, so effectively you have the same weight as with the SGD term. But the bigger difference is, if you look at this green box, the noise term doubles. Now this is interesting because if you look at the analysis of momentum methods in non-convex papers, in virtually every analysis, this noise term grows with your momentum. So if your momentum is 0.9, typically the growth here would be 1 minus momentum. So you'd actually, over 1. So you'd actually have a 10-fold growth for 0.9 momentum. But you can actually do this tighter analysis when you write everything in the SPA form. And you also get this extra term in the blue box, which is not problematic because it's actually a negative term. So you can kind of think of it as only offering improvement. And in fact, you can dig into the details of this, like how does this blue term behave? And you come with some really interesting things. And I do that in the paper that I cite at the bottom here, which is kind of worth looking at. So the main thing you can see is you get this intuition behind why momentum methods work well. And the intuition is really simple. If the gradients are uncorrelated statistically, so this is something we can do to do very simplified analysis rather than assuming our gradients between steps are related, just assume that they're uncorrelated random variables. If you do that, this term is effectively negative of half the noise in the method. So when you do that, if we go back to the previous slide, the fact that the noise here is double, that gets cancelled. So you end up with the SPA method giving virtually, like there's a tiny difference in the constant, but you get virtually exactly the same noise as SGD. And I think this is what happens in practice, because you can actually measure the correlation between gradients, and we know that momentum methods don't have higher noise than SGD in practice on these non-convex problems. And this is what you see here. This appears to be the reason why. But interestingly, when the gradients are correlated between steps, this term becomes a large negative factor. And when you have a large negative factor in the Lyapunov analysis, it actually results in a tighter bound. So this is when momentum helps, when gradients are correlated. And gradients are typically correlated at the early stages of optimization. So what I'm trying to argue here is that this kind of Lyapunov analysis gives a very practical understanding of why momentum works in the non-convex case. So we get that momentum significantly speeds early convergence where gradients are heavily correlated statistically, and then does not hurt convergence at the later steps. And one thing I do in this paper is I just check, like, when do the gradients become uncorrelated, and it turns out it's actually very early in the training of most computer vision models. We're talking like less than 1 epoch. And then what you can do is you can just try turning momentum off past that point. And if you do that, you'll actually find that it has no effect on the final convergence performance. So you really only needed that momentum for 1 epoch. And this is for like ImageNet training, CFR10 training. Yes, question?
Yes, thanks. If you go back to the previous slide,
yes.
that is the motion representation. So this is the uncentered second moment. So at the early stages where the mean is potentially pretty large, this can be large, Your
Yep.
G squared is also the uncentered case, or is that the centered one in SGD?
Yeah, that's a good question.
That's also uncentered.
Uncentered, yes, yes.
Okay,
Yeah,
so it's literally the same, say
Yeah.
for a factor 2. Okay.
Yeah.
Okay, cool. Thanks.
So the surprising thing is, the more you dig into this kind of SPA form and the analysis that you get in the non-convex case, the more it makes sense. And in fact, what you find, let me go back to the plot here that I had. You actually find this scheme where you linearly decrease the learning rate and linearly increase the momentum that I'm suggesting that would be reasonable with this SPA form. In fact, it's exactly what you need to keep the remainder term, which I've suppressed in the notation here. It's the RK. If you want to keep RK negative, sorry, that's wrong. Sorry, the term in the blue box, not the RK term. If you want to keep the term in the blue box negative the whole time, so it doesn't contribute in a bad way to your Lyapunov function, so you can effectively ignore it. If you want to keep it negative, that is good. You need to decrease the learning rate gradually. So this cliff schedule we use with SGD doesn't work in this analysis. You need to decrease it gradually, and you need to increase the momentum gradually as well. And you can in fact work out exactly the bound on how fast you need to decrease. I mean, in practice, there's not much advantage to decreasing the learning rate suddenly versus doing it over a few epochs. I've done a bunch of experiments with this with ImageNet CFAR10. If you just decrease your learning rate over like 5 epochs rather than at a cliff at a certain point, you get effectively the same final test accuracy. So this idea of decreasing it gradually makes a lot of sense here from the theory. And the other thing you realize is exactly how large you can have your momentum. And what you find out when you do this, you dig in the details here, is you can effectively increase your momentum until you start hitting a point where your learning rate is restricted by the curvature of your problem rather than the noise in the problem. What I mean by that is typically in non-convex problems like this, we use a learning rate that's smaller than what we would use in the non-stochastic case. And if you look at the analysis, that'll be like by a square root n factor, n being the number of steps. And if you try and increase your learning rate to be larger than the difference of these two rates, that's when you run into trouble. So you can effectively, according to this analysis, make your momentum close to 1, 0.9, 0.99, 0.999, until that ratio between 1 and the value starts to approach that gap between the stochastic and non-stochastic step sizes. So yeah, it's surprising how much insight you can get from a Lyapunov analysis of momentum in this SPA form, and this is one of the reasons why I think it's kind of intuitive. And I didn't want to spend the whole presentation talking about this, so I haven't got an enormous number of slides on this actually. But I'm happy to answer any more detailed questions about momentum and particular this paper at the end of the talk. So I'll move on for now, so I can stay on time. So yeah, I want to talk about the Madgrad method, which is what has kind of been my focus. It's got some interesting properties, and I hope that we can kind of use it to understand better adaptive methods for non-convex optimization. So essentially, Madgrad arose from me being frustrated at Adam. Adam has convergence theory that doesn't really cover the situations we use it in. There are very simple counterexamples where it just fails completely, and it's known to not generalize well on common benchmark problems. So, if you apply it on ImageNet and CFAR10, it just doesn't work very well. So the kind of plan of attack here was, can we take a method like Adagrad, which has very strong convergence theory, and modify this, adapt it to bring it up to the performance of Adam. And I think we got there. In fact, it often performs better than Adam. And I'm going to kind of walk through this sequence of modifications that we took, Sami and I, to get to the Madgrad method. So the first thing is we kind of build upon dual averaging. And dual averaging is one of the most misunderstood methods in optimization. And I think it's really understudied in a lot of these settings because people always use it with regularizers. And this top equation here is the standard dual averaging update. This is kind of like the general case here. We're still assuming Euclidean norm. But essentially, this form of writing it, where your iterate is given by the solution to a minimization problem, it's interesting when you have some sort of complicated structural regularizer. But in the non-convex deep learning case, we don't have those. So we're just going to look at what this method does in the simple Euclidean case. We're not even putting an explicit regularizer in there. So we're assuming any regularizer we're using is within the F. It's collapsed into it. And you end up with this equation in the middle of the slide. And this is interesting. The reason why it's interesting is when you kind of survey a lot of the non-adaptive methods used all over the field of optimization, when you strip out all the kind of complexities to those methods, you usually just end up with gradient descent, or in the stochastic case, stochastic gradient descent. And dual averaging is interesting because it doesn't collapse down to gradient descent or stochastic gradient descent. Now, there are certain hyperparameter settings where it will collapse to it, but it doesn't in this general case. And the reason being is the point, your iterate, xk plus 1, it's given by this relation from the initial point x0. And in this relation, we have this 1 over beta k plus 1 term. And beta k plus 1 is an increasing sequence. So what we do is we take the sum of gradients, and at every step, we decrease the contribution of each gradient to the current point. Talking about all past gradients, we decrease the contribution of all of them. Compare this to regular SGD in the box at the bottom. Now, this is writing SGD in terms of the initial point, which is equivalent to the usual way of writing and assuming a fixed step size. Here, all the gradients are equally weighted. And if we use the decreasing step size of SGD, we would only decrease the contribution of new gradients. We don't decrease the contribution of old gradients. Compared to in dual averaging, we're always decreasing contribution from all of them. Do we have any questions here? No? So yeah, I'm surprised how rarely this Euclidean dual averaging form comes up. Now, why is this interesting from a optimization perspective? Well, one reason is if you actually look at the theory behind Adagrad, the dual averaging form of Adagrad has a very elegant theory. All the equations follow very nicely. It's very nice if you're the kind of person who appreciates that. Their non-dual averaging form, on the other hand, kind of seems like they did the dual averaging form first, and then they tried to get things to work in the regular form, and they kind of got it working, or the theory holds, but it's a little bit ugly. And it really feels like the natural form is the dual averaging form.
There's a question.
Aaron, yeah,
Yeah,
I have a question. Doesn't it collapse to SGD with a decreasing step size, though?
No, because we effectively are downweighting all past gradients. So as beta k plus 1 grows, I should say that, sorry, I should say this. When you use this dual averaging form, you would normally not decrease gamma at all. The reason being is you don't have to. In the convex case, this method is a anytime algorithm. So the beta sequence is effectively a decreasing step size. And in fact, when you look at the analysis of dual averaging in the convex case, the constants you get are similar to the anytime versions of SGD, where you use a step size that decreases like at a 1 over square root k plus 1 scheme. So yes, in fact, if you try and change the learning rate gamma in this dual averaging method, it will immediately diverge. So never do that, at least when written in this form. It doesn't work. So yeah, it's very different in that regard. It's probably a bad idea. In fact, on this slide, I really shouldn't use gamma in the two cases for the step size, because yes, you can't treat them in the same way.
Thanks.
Yeah. Sorry, that's confusing on my part.
Just
Yes.
one, just
Yep,
to add,
Yes.
is it correct to say that if you were thinking of 1 over beta k as the step size sequence, then in regular SGD, the 1 over beta k's would appear inside the sum as opposed to outside?
Absolutely, yeah. So yeah, you should really think of the beta k as being 1 over beta k being the effective step size. Yeah. But this is something that I wanted to kind of attack as well. So I'm going to talk a bit more about these step size sequences in the next few slides. Okay, so one of the main things we looked at here is the issue with including all gradients with equal weight in the dual averaging method. The problem with this is newer gradients give more information. I think this is kind of like an obvious thing. In the convex case, it turns out they don't, but in the non-convex case, it's implausible that that new gradients do not contribute new information. So we want to upweight newer gradients, and this is kind of heuristic that we want to do this. You can actually still do the analysis in the convex case when you upweight newer gradients, but you get a very slightly worse constant, like factor 2 or something like that. So it's not a huge hit to your effective convergence rate. But yeah, this is kind of heuristic. So the change we have here is we're upweighting gradients. So if you see in the summation here, we multiply each gradient by its iteration that it was visited at. So square root of I plus 1 is square root of the iteration it was visited at. And this is kind of a very gradual upweighting. And we move the step size inside the summation. And this is exactly based off our discussion on the previous slide. It makes no sense to have a varying step size outside the summation with dual averaging. If you implement that, it just immediately diverges. So we put it inside the summation. And now you end up with this alternative method with front-weighted gradients. And when you do this, it's really worth thinking of this as still being a variant of SGD. If you look at this bottom equation, we can break it apart and still write it as an equation that resembles SGD. Here we have this gamma I gradient term. Looking at the bottom equation here, the gamma I gradient term, it's just like in SGD. But we have this other term at the end here. And this other term is a kind of regularization penalty kind of. You can see that we're essentially effectively decreasing the weight of past gradients, but keeping the weight of the most recent gradient we visited constant. And this shrinks the sequence that you're visiting towards x0. Now, what is the advantage of this? We now have an equation where we can actually set gamma I as we normally would in SGD type methods. And this is really an important thing. Now, one thing you find out very early when you try and train CIFAR10 ImageNet using these kind of decreasing step size sequences, like 1 over square root k plus 1, it doesn't work. You get terrible generalization performance when you use those sequences. Now, the fact that dual averaging has an implicit sequence where it decreases the step size in that way enormously hurts performance on these practical problems. So by doing this modification, where we now always introduce the most recent gradient with a weighting of exactly gamma I, we have now allows us to use standard learning rate schedules that we would use with SGD. So you can use the cliff schedules where you decrease the learning rate by a factor of 10. And in fact, that's what we do in some experiments. Sammy and I did that, and I'll show you some plots in a slide or two. But let me explain a little bit more about this decaying regularization that I mentioned, because this requires a little bit of thought. So what is actually going on? Well, when we decrease the weight of the previous gradients, we're shrinking towards x0. And you can actually just rearrange this and write this as if you're optimizing a different problem. And this problem you're optimizing is a problem where you have a squared regularizer that pulls the iterates towards x0. And this regularizer has a certain weight alpha k in this notation. And if you work out, you do the math, you get that this is equal to 1 over k plus 2. So your regularizer decays kind of gradually during optimization. And it's kind of surprising that in the convex case, you can add this regularizer and it has no negative impact to the convergence theory. You would expect that whenever you add additional regularization to a problem, you're in some sense loosening things, but in this case, it doesn't loosen anything at all. And yeah, the nice thing is this change makes all of a sudden you get competitive performance on image problems with SGD. And this is interesting because dual averaging by itself does not work on these problems. So let's look at CIFAR10 as an example. You can run these numbers for other problems where people typically use SGD. But if you just use dual averaging by itself, terrible performance, you get 87% accuracy with this network. Just adding momentum on top of it, and this is the type of momentum I described earlier in the talk, you get 90.8%. And further using this front-weighted gradient sequence, which is quite key, you can push this up to 95.58%, which is effectively what you get with SGD. It's a little bit higher, but that's really noise on these kind of problems. It's usually a 0.2, 0.3 kind of noise you can expect here. So after we kind of realized that, we were thinking, you know, can we then put the Adigrad style adaptivity on top of this dual averaging? So we're kind of combining all these Lego blocks together. We took dual averaging, we added front weight gradients, we added the momentum, this exponential moving average momentum that we described earlier. Now we're going to try and add Adigrad adaptivity on top and see what we get. And this is a little bit tricky because you can't use the same kind of denominator sequences that you would normally use with Adigrad. So this equation in the top here is what we kind of settled on here. So we're still weighting the gradients by square root of the current step. But to get this property that we want, the property that we can use regular step size sequences that we'd normally use for SGD, we normalize the denominator with a cube root. And this is a little bit odd, and it arises just partly because you just want everything to, all the constants to match so that the step size behaves as you want, but you can also motivate it from a different scheme. Now, in the Adigrad paper, they originally motivate their denominator by the fact that it solves this minimization problem that they write out on the left bottom of the slide. And this is essentially and you don't look at the future when you're solving this problem. So it's looking at the past gradient sequence, and we want to find a denominator S that minimizes, while the S's are positive, minimizes the sum under a linear constraint. And this linear constraint, essentially, you can see there, it's a dot product of S with 1. So that's effectively just the sum of the S is less than C. Now, what we do in our situation is just use a squared norm of S. So we're penalizing the squared norm of S. And this is one of those weird things you get when you read the Adigrad paper. Like, why do they use this linear constraint? And you know, you can justify that why it's reasonable, why it's not. But certainly, like, a quadratic penalty is equally reasonable, and that's what gives you this kind of cube root denominator. So this is a little bit hacky, and it's part of this cube root denominator. It's got some reasons, some motivations for why you might want to use it, but you could certainly use different denominator sequences here. And in the Adigrad family of methods, you have an enormous amount of flexibility in how you choose the weightings of gradients and how you choose the denominator. And you can prove properties of practically any sequence that you use here that's reasonable. So I don't want to say this is the only way to do it, but this way seems to be motivated theoretically and in practice. So the whole method is the following: the combination of all these approaches we just talked about. And I'll walk through it quickly. So line 4, lambda sequence. This is just our step size, our gamma k, and this is expected to follow standard SGD conventions. So you might decrease it at certain epochs, like if you're training ImageNet, decrease it at 3060 epochs, and multiplied by step count plus 1 square root. So this is that gradient weighting that we're talking about. And we accumulate 2 buffers. This is very much like in Adam, where you accumulate a gradient sequence and a squared gradient sequence. You do exactly the same thing here, but with weighting. So you weight by lambda k. And this is not a moving average sequence, it's a sum. So you can see that if you're in Adam here, you would weight by a beta 1 and a beta 2. We have no beta 1, beta 2 here. And then you just use, in line 7 of the formula, you use this cube root denominator weighting. We put an epsilon there just because it helps with some numerical issues. Some people argue that the epsilon in Adam is essential for performance. That is because Adam's a broken algorithm. This algorithm here, the epsilon is not really that necessary. It's more just to avoid divide by 0. So you do not want to use large versions of epsilon here. And for line 8, we use the exponential moving average momentum, this SPA momentum that we talked about earlier in the talk. And the nice thing about this method is you kind of get all the benefits of adaptive methods like Adam, but you still maintain the generalization performance of SGD. And you can show this with some experiments. Let me just go through quickly some experimental plots. So we have a classic ImageNet test problem. And here you can kind of see what you might expect. So Adigrad performs poorly on this problem, extremely poorly. You get final test performance of about 68.5%. Adam is better than that, but still terrible. And people attribute this to Adam potentially overfitting or converging too quickly. That's actually not correct. Like if you look at the training loss on the right, it's really not converging quickly. compared to the other methods. And you see, yes, like SGD and SGD and MadGrad give very similar final test performance here, with MadGrad kind of beating it out, kind of the midpoints of optimization. And this is kind of what you would expect, because we're looking at generalization performance. This is held out test performance. Fast optimization doesn't necessarily mean better generalization at the end. And this is always a problem when you're trying to sell your optimization method, because often if it's too fast, it might generalize worse. In this situation, we've done a hyperparameter sweep of the weight decay, just to make sure that each method is using the correct decay, so that you don't have this issue where your method appears to underperform. And I did the decay sweep on all the methods, including Atom and Adagrad, so that they're really kind of performing as best as they can here. And you get similar results for CFAR 10, where you can see Adagrad and Atom performing poorly, SGD and MadGrad performing well. So this is kind of interesting. Like, I don't have a full explanation. I certainly don't have like a theoretical framework that explains why these methods generalize better. I do suspect that some of the problems with Atom here are just due to it potentially being not necessarily like a non-convergent method, but it follows a very different path than gradient methods do. And particularly the exponential moving averages you use, they change so rapidly during optimization that you can kind of veer off into various directions and, maybe end up in worse minima and things like that. So I don't claim to kind of have a solution to generalization here, but empirically it works pretty well on these problems. And you can still test it on problems where people would normally use Atom. So it wouldn't be much to claim that it just matches SGD if I don't always also test against problems where Atom works well. And you can do this pretty standard problems. This is a large-scale masked language model, these kind of BERT models. I'm sure all of you have seen pictures of Elmo and Bert in presentations while you're zoned out thinking about your own problems. This is one of those models. And you see that this MadGrad method is a little bit slower initially, and then kind of levels out and matches the performance of Atom. And that initial a little bit slower performance is probably due to the weight decay in the method that decreases over time. So as I mentioned before, with dual averaging, you have this implicit weight decay decreases over time. And that will give you, artificially bad performance at the early stages. But in fact, it's actually helping you at the later stages because you find potentially better local minima by regularizing early. And this is, of course, a problem where SGD performs really poorly, the same with Adagrad. I also have kind of this toy problem that I worked on. For a while, I was collaborating on the fast MRI team, working on MRI image reconstruction. And the model we have there is nice because there hasn't been this enormous focus on improving the models in these image reconstruction tasks compared to computer vision. We know when we're working on ImageNet and CFAR 10, thousands of researchers have tried different models on these problems to try and find the best model. And often this leads to models that are easy to optimize because they tend to work well. This image reconstruction problem, people use UNet type models, which have very terrible properties from an optimization point of view, and trying to optimize them using SGD runs into all sorts of problems. And even with Atom, it doesn't work as well as we want. So on this problem, the MadGrad gives really good early performance, a lot more stable than Atom, and slightly better generalization performance. All these numbers are pretty similar in terms of SSIM. That's kind of a property of that metric for measuring images. So small differences in SSIM can be kind of large in the final result. So yeah, in terms of why it generalizes well, still not clear. I do think it's a combination of the implicit regularization together with the fact that it has good convergence properties in the convex case. I think I actually forgot to include the slide with the actual convex convergence theory proof, I think, maybe. But yes, so essentially you can establish convergence rates that are very similar to Adagrad convergence rates in the convex case. Yeah, so Adagrad similar to Adagrad in the convex case. I do not have a convergence theory for the non-convex case that's satisfying. We kind of have some very loose bounds that really don't tell you anything about the performance of the method. And this is kind of an open problem. Analysis of dual averaging methods in the non-convex case is pretty wide open, and even adaptive methods generally, the theory is getting there, but we still have a lot of limitations. But yeah, the fact that it has very strong convergence properties in the convex case is something satisfying. Even though, as I talked about before, we use different momentum sequences in those situations. So now would be a good opportunity to ask any questions about the MADGRAD methods. Let me bring it back up. Yes, there's a question.
Yeah, I have a couple of questions.
Yeah.
So first of all, regarding, I know you don't have answers, but I want to ask about particular, I guess, intuition that has been in literature for a few years now regarding adaptive methods and their generalization, and in particular adaptive methods that do this kind of ADAGRAD style adaptation, where you have a different step size for each variable, right? And one of the arguments that were put forth in one of the papers I remember is that this kind of property allows you to leave the span of the data, meaning that when you do regression, for example, least squares regression or something like that, if you use gradient descent, all of your gradients will be within the span of the data. If you use an adaptive method that has this particular property, some of your gradients will not be in the span of the data. So then, and that was used as a potential argument as to why some adaptive methods seem to not perform as well. Why? Because the argument there was that in least squares, the minimum norm solution, when it's an underdetermined problem, the least norm solution is generally understood to generalize better. So if you leave the span of the data, you will end up with a solution that's not minimum norm in some sense.
Yes.
So how does this kind of intuition work for you?
Yeah. So yeah, I actually think those results have a lot to say here. They do tell you something about why those adaptive methods don't generalize well. What you want to see here is when you're using dual averaging based adaptive methods, you're constantly shrinking the iterate towards x0. So if you do what people do with the SGD case and what those analyses assume, if you initialize at the 0 point, you're shrinking towards 0. So I haven't actually worked through the maths there, but I'm pretty sure if you use dual averaging versions of adaptive methods, you do not have that problem, at least asymptotically. If anybody knows anything about that, please chime in. I haven't done any analysis regarding that, but yeah.
It's that property, if I understood correctly, you're retroactively down weighting your old gradients, right?
Exactly. Yeah, and you can see it in the formula, right? We're always shrinking things towards x0. So yeah, that's kind of like an interesting area of analysis to potentially do, to potentially work on. So yeah, I think those arguments just don't apply for these dual averaging forms. And this is one of the nice things about dual averaging. Yeah. Yeah, if you want to see the analysis for the convex case, check out the paper. It's not very complicated. So you get the nice property that we talked about earlier in the presentation, where typically for a stochastic method, you would normally analyze a ergodic average of the iterates, whereas here we can actually analyze convergence directly of the X sequence because it's effectively an average. So that's one of the nice kind of results you get there compared to standard ADAGRAD or other stochastic methods. Yeah, so I encourage people to try this method out and potentially extend it, because there are some kind of unsatisfying aspects to it. I'm not sure if it's kind of there. You know, it works really well on these problems, but I think it's a good foundation for kind of further optimization work. And I think it's particularly dual averaging methods in the non-convex case have a lot of potential. Any further questions about this? No? Okay. So wanted to kind of, this is when I move on to the ranting part of the presentation. I'm going to propose an anthropic principle of deep learning. It's a bit tongue-in-cheek, but basically, some of you may be familiar with the anthropic principle of life, that the universe we're in must have properties which allow life to develop, otherwise we wouldn't be here talking about it. Well, I claim that a similar property holds for models that appear in deep learning papers. Essentially, any model that appears in deep learning paper must be optimizable with the methods used in the paper. Otherwise, they wouldn't have discovered the model. And the impact this has on us as optimization researchers is that you may not be able to get much additional bang for your buck from using different optimizers. If it so happens that the model is so co-adapted to the optimizer that they use in the paper that it works worse with other optimizers, then we're kind of stuck in this regard. And I think this is actually something that has very much happened in practice, particularly the models people use on ImageNet and CIFAR10, the ones we do all our plots on, those models. They're co-adapted so heavily to SGD that it's very difficult to get any kind of real improvement. And much of the improvement you see in papers is kind of like wishy-washy at best. It's not like a real improvement. There's often so much noise in these experiments that you can't really see any true improvement. And I do realize I just showed you plots on these problems where my line was above the other lines, and I'm claiming it's better. So certainly, I'm very guilty of this as well. And this is also true of other models, like the transformer models that people use are kind of adapted to the Atom optimizer, and it's not even clear that they should work with other optimizers. I don't think that you can just use a better optimizer and expect it to be faster on these problems. And I think when we're developing new optimizers in machine learning, the interesting thing to do is really to look at problems that we can't solve or we can't optimize quickly with existing methods. And there are some interesting ones there. So for instance, a particular problem that I find really fascinating is large batch training of ImageNet models and related. And in this setting, you start to get to the point where noise is less of an issue and curvature of the models is more of an issue. And this is one of the secrets of ImageNet and CIFAR10 type models. In the standard regimes we train them in, they're essentially completely noise dominated. And noise is what dictates the learning rate that you set. And for this reason, doing any kind of second order tricks on those models has very little impact. But when you go to this large batch setting, the noise is minimal and you can start to get advantages from using more sophisticated optimization algorithms. So if you're thinking of doing some experiments on ImageNet, consider doing them in the large batch case. And you don't need a cluster to do that. You can just simulate large batch training by doing multiple batches in a row between steps. And other kind of problems, like there's some vision transformer problems that have been developed recently that are harder to optimize than the usual models we use on ImageNet. So just want to complain a little bit about this. And having said that, if you don't do experiments on ImageNet and CIFAR10, your paper won't be accepted in conferences, so you need to still do those as well. And the third kind of quick part of this talk, after the ranty bit, is I want to talk about preconditioning of neural networks. And I put that after the rant because I'm going to be talking about preconditioning models for computer vision. And you can't really get any advantage from improving or preconditioning these models with the normal batch sizes for the reasons I just described. So this is kind of like a little bit of theory that I find interesting, but not actually particularly useful for these networks. And maybe it's useful for the design of new networks that have worse conditioning. But I find it interesting anyway. I'm going to go through it very quickly. I think we're going low on time. But essentially, there's a way of preconditioning networks that is maybe not very well known. Essentially, rather than trying to multiply by some matrix, how we typically precondition in optimization, instead you can add weights in your network. By weights, I mean simple scalars. And you can set these scalars so that the output of your network is identical at initialization to what it was before. But by setting the scalar at a value like 2 and then decreasing the weights before that scalar by the same factor, you actually change the conditioning. And by that, I mean the Hessian or the values of the Hessian corresponding to those weights in that block. So this gives you a way of changing the Hessian in a network without changing the output of the network, which is what preconditioning is. And the nice thing about this is you don't end up with like hideous, complicated optimizers that are slow to use. And you can actually get people to adopt your code because you can just kind of send them a model file and say, hey, drop this model file in instead of your usual ResNet 50, and they might actually do it. So it's kind of an interesting idea. And what I want to talk about briefly is kind of how you can set these scaling constants. And I have like a bit of a theory here. And essentially what I'm going to assume is we have square images. So we're working with convolutions, but with no batching. So we have batch size 1. And we have a number of channels n. So rho is spatial dimension, n is number of channels. And I'm going to define this, this constant, I'll call the scaling factor. Var sigma here is the scaling factor. And this is just essentially a product of quantities that we see here. And I'm going to use a lot of notation here by working with an entire vector, and I'm just actually taking the square of the vector. And by that, I mean element-wise square. And I'm taking the expectation of this. And this expectation is an expectation at initialization, assuming random inputs, random initialization of the network. So this is kind of like a horrible simplification in order to get a simple equation. And the very broad claim I'm going to make is if you can balance these var sigma everywhere in your network, by that I mean that every layer, when you calculate the value of this equation, will be with the same value. If you can balance that, you have an approximately well-conditioned neural network. And you need to make a bunch of assumptions for this. I'm not going to go into the details of this, the assumptions at the bottom. But there's a justification for this. In fact, 2 justifications. So the first one is very much a kind of hand-wavy one. And what I'm going to do is look at this quantity nu. Now, this is just a ratio of essentially an expectation under all these hideous assumptions I made of the backpropagated gradients of the weights compared to the weights themselves. And this ratio is kind of crucial. It captures the magnitude of your steps when you're doing optimization. So one thing you can actually prove is that if you balance that factor on the previous slide, the scaling factor var sigma, then your nus, this ratio everywhere in the network, will also be the same for all layers. But how does this link to the Hessian? So to link it to the Hessian, you've got to do even more approximations. Let's get through this quickly. But this is kind of the claim I'm going to make without an equation because it's a little bit messy to write out. But essentially, if 2 layers have the same scaling factor before and after the layers, so the layer maintains the scaling factor, then you have in expectation in kind of the limit of large layer width, but in fact, it really holds for modest size layer widths as well. You have that the average squared singular value of the respective diagonal blocks of the Hessian for these layers is the same. Now, the average squared singular value is kind of a reasonable measure of the size of a block of a matrix. It's closely related to the Frobenius norm, which would be the kind of the unnormalized version of the same quantity. And you can very easily kind of run some simple examples. And in this case, I essentially take a LeNet network, and each of these squares is a weight block. This is the Hessian here. So the diagonal is the diagonal blocks of the Hessian corresponding to each of the weight matrices in the LeNet. And using the scaling factor, if you balance the scaling factor everywhere, you end up in practice with these blocks that are of similar average singular value magnitude. And this is not the case with the standard initialization, although it's not, you know, horrendously far off. And since I'm kind of, I think I'm out of time, I'm going to not talk too much about this, but essentially, this is kind of like an interesting principle, and the main consequence of it is you get an interesting initialization factor. So initialization of neural networks is one of those things that's bugged me for a long time because the papers on this always use very hand-wavy arguments. For instance, you know, we often do this K-mean initialization, and the purpose of that is to keep the this kind of squared magnitude of the activations the same everywhere in your network. So before and after a layer, squared activations, you want them to be of the same magnitude. Why? Like, what is the justification for that? It's one of those principles that sounds good until you actually try and dig into it. Like, why would we actually need that? Now, you do want the output of your network to be within a reasonable range because you're probably feeding it into a softmax function or something like that. But you can easily achieve that output scaling by adding an extra scalar to the exit layer of your network that just scales everything down by a certain factor. So there's no need to have this true in the middle of the network. And what you get when you try and balance these scaling factors that I'm proposing here is you get this kind of unusual geometric mean of the fan in and the fan out as the initialization should use. And you get a slightly different dependence on the kernel size. Maybe we should stop for questions here. Any questions about the scaling factor and the initialization scheme? I don't have time to kind of go into the full details of this here, but I am making the kind of grand claim that we've been initializing all of our neural networks wrong for several decades. So if you're suspicious of that, check out the paper and see if you're convinced by my argument. Now there is a scaling factor C here on the numerator, and you can set that to whatever you want. You probably want to set that so that the output of your layer doesn't explode after every layer. So you can set that to a factor 2, like they do in the K-mean schemes, or you probably even more likely want to set it to 2 over K. K is your kernel width, so that your output is very similar to what you get with the K-mean scheme overall. Yeah.
I don't know if you want to say a word, Aaron, just on the last part of the talk there. I don't know if you want to say a word about how that preconditioning interacts with batch norm or things like that.
Yeah, the answer is it doesn't interact well with batch norm because batch norm just changes the scaling of your output. So this kind of initialization is most useful in a situation where you're trying to design networks that don't use batch norm. A lot of practitioners are kind of interested in this problem because batch norm is a major performance hurdle, and there are some recent papers that essentially are able to get rid of batch norm and match the performance. And in my preprint, I essentially modify one of those schemes to use this initialization that I'm suggesting here and show how you can do that and keep all the scaling factor balanced and get good performance. But yes, if you just use this with batch norm, it all cancels out really in the end anyway. So yeah, batch norm not really compatible with this scheme, unfortunately. Yeah, so that's everything I wanted to cover. I know it's kind of like a little bit of a grab bag of things, but thank you.
Thank you very much, Aaron. It's great.